Hello, welcome everybody. Let's get started. Thank you very much for joining me today. My name is Gunther Hagleitner. I am a Director of Engineering at Hortonworks. I focus on SQL and BI. And today we'll be talking about LLAP, about how to achieve sub-second queries in Hive. And before we get started, I'd just like to see a quick show of hands. Who here has or is currently using Hive? Oh. Okay, so that's about everybody in the room. Now, we've been talking about LLAP for a couple of years now, but we're just now getting a GA version out into the market. So let me ask you this, who here has played with LLAP before? Who has tried it out? Who has deployed it? All right, very, very few people. So I'm hoping I can change that, A, by showing you what it can do, and B, by kind of showing you towards the end of the presentation how you can quickly spin up LLAP and play with it yourself and check out your own workloads on that. I don't know if any of you saw Alan Gates' talk this morning on enterprise data warehousing with Hadoop technologies and Hive. He was basically complaining that a lot of the query engine guys, all they do is show graphs on how their engine performs on TP-CDS. So just to be clear, I am that guy. I will show you a lot of graphs on TP-CDS and how the engine behaves. But I'm hoping that it will still be interesting for you guys. Anyways, I'm going to start with a quick demo. The demo is basically going to run a TP-CDS query, obviously. It is a reporting query that we're going to be running on a 1 terabyte data set. And we've used 10 nodes to run that. And I will be running the query, well, this is a recording. I have run the query without LLAP and then with LLAP as comparison. And that kind of gives you, I hope, a feel for what that looks like. So let's jump in. You can see at the very top, we are turning off LLAP and running query 55 from TP-CDS. And now it's running, and you see the progress bar elapsing. So it took about 10 seconds. Now we're running it with LLAP turned on, and we run it again. And it's already done by the time I say this. So these are the two progress reports of the query. One took 10 seconds, one took less than a second. So the difference is quite striking. And if you're playing with live data, if you're running a lot of queries, a difference like this can make or break your day. You can run a lot more. It feels a lot more interactive. If you're running Tableau or some other tool against it, obviously that's very nice. Another thing you can see from that is that I didn't change tools, or both of them use the Hive CLI. I could, both of these ways of running Hive, LLAP or container mode, work with the same front end and the same clients. So if you're using Tableau, if you're using Hive CLI, if you're using your own SQL front end or SQL client, that is not going to change. LLAP is all under the hood. So another thing is you might ask yourself, why would anyone run containers if it's 10x slower in this case, and why not always run LLAP? Good question. But the difference is that when you run Hive in container mode, Hive will basically, if it's not doing anything, if it's not running any query, it is not going to use any resources on the cluster. It will release all containers. It will give everything back to Yarn, and it will let Yarn give these resources to other to Spark programs, to whatever you want to run, to Pig, other Hive queries. So Yarn really can share these containers, and when the query is done, it will give them back. In the LLAP mode, this is more like an always-on mode. You will give LLAP a certain part of your cluster. You can give it all of it. You can give it part of it. And it will hold on to that stuff. And it will use all the memory you give it to cache things. It will use all the cores that you give it to run stuff asynchronously. And it will permanently use up that capacity. But what you get in return is a much more interactive experience from Hive. So I'm now going to spend time, go over a few charts, running TP-CDS queries, and kind of showing what we've seen here over a wider set of queries. So this is Hive 2 LLAP with just many more queries of TP-CDS. I'm using 10 terabyte scale here. 10 nodes again, 256 gigabytes per node, 32 cores per node. The green lines that you see here is the Hive, the green bars is query times in second achieved by Hive 2. the kind of line that is trending down is basically the improvement over Hive 1. So if you, on the left, for instance, see 15 improvement over Hive 1, that means Hive 1 took 15 times longer to run that same query. So what can you see from that graph? So TBCDS, if you're not familiar with it, by the way, has a wide range of queries. Some of them are interactive queries, some of them are iterative queries, some of them are reporting queries, and some of them are kind of machine learning or deep reporting kind of queries that scan the same set multiple times, maybe join fact tables together and do stuff like that. So what you can see is for a lot of queries, we're doing very, very well, and we're pretty fast running these queries. The improvement over Hive 1 is tremendous. I mean, it's an average 5x. In some queries, it's 15x. Not everything is going to be sub-second, obviously. If you're doing heavy lifting, that is still going to be heavy lifting. We're doing better, but it still takes some time. So queries like 64, you will have to do different things if you want to get the runtime down, which is possible. There's techniques. It's just LLAP alone is not going to help you with that. But overall, pretty happy with that result. Now, here's, as I said, here's just one type of query in TPCDS. It's the interactive queries. And I ran it on a smaller data set. It's a 1 terabyte data set. And what you can see here is that, again, you get up to 25x performance gain with Hive 2, just enabling LLAP. And all of the queries are super fast, within 5 seconds. That's what we usually try to get to, because after 5 seconds, people are wondering if they should go for a coffee if the query is still running. So we're trying to keep it in that range. So that was comparing Hive against itself, basically. Hive 1 with containers versus Hive with LLAP. Now, how does it look against other engines? This is against Apache Impala. It's another SQL engine for big data, mainly contributed by Cloudera, now Apache incubating. So what does it look like? So this engine is also purpose-built, by the way, for these interactive kind of big data queries. So what you see here in the middle of this chart is basically that there's a number of queries that are in the 10-second range, and Hive and Impala seem to be performing pretty even on those. On the left side, you see the queries that Hive is doing better. On the right side, you see queries that Impala is doing better. There's some they are doing better, some that we are doing better. In this particular benchmark, it turned out to be 50-50. We still feel that Hive is scaling better, because if you combine if you look in the entire benchmark and you add up how much time it took to run it, Hive is actually quicker end to end. And that's basically because some of the truly large running queries, Hive was just scaling better and still taking a lot of time, but coming out quicker than Impala. We've also compared it to Presto, which is gaining more popularity every day. The problem with Presto was when we started running it, it became clear pretty quickly that they're just missing some of the performance optimizations that are required to run this benchmark. They don't do dynamic partition pruning. I don't think they're doing cost-based join reordering and stuff like that. So if you fail to do these things, you end up taking a very, very long time, because you need to scan a lot more data than all the other engines. So that's basically what we found. Now you can go in and say, fine, the optimizer doesn't know what he's doing, but I know what I'm doing, so I can rewrite the query, and we've done that too. And you can bring down the Presto runtimes quite a bit. But we found that we're still faster in scanning these queries than Presto was. Okay, so that's kind of the comparison against what else is out there. Just as an example, Presto and Impala. Next thing to look at is kind of how does the system behave if you have more than a single customer, because a lot of these benchmarks you run as a single user are using up the entire cluster. So what we found is here, this looks like a very complicated graph. It's really not. It's in red. So we ran TPCDS queries. We took with a 1 terabyte data set. We took all the TPCDS queries and we kind of ran them in a loop and ran them in parallel. The red dots show what happens if you run 5 queries in parallel. The kind of purple one is if you have 25 queries in parallel, and the yellow one if you have 100 queries in parallel. All of them on 10 nodes of LLAP. Obviously, the more concurrent users you have, on average, the queries will take longer. And what we found is it turned out to be linear in the number of concurrent users that the average of the query runtime degrades. Now, the other thing you can see here is that the queries kind of spread out more, and the max kind of moves out further too. And that's kind of on purpose, because what LLAP is trying to do is it's trying to take into consideration how long a query will really take on the cluster. And it's trying to give resources to short-running queries quicker in order to maintain an interactive feel on the system, even if there's like long-running queries in the back. So that's why some of the DPCS queries that just take a lot more resources and take a lot longer will be punished in favor of some queries that we get out sooner. So that's what you're seeing there. There's another kind of linear scale involved with LLAP, which you can see on the left side there. So the average, we said, like moves with the number of concurrent queries, but it also is linear in the number of nodes. So that means if you start adding more and more users to your system, and you start getting lower and lower response times for your queries, if you just add more nodes to it, you can regain the performance and the response times. Again, the maximum behaves a little bit different on the right side. It's not exactly linear. So the max will scale out a bit further. OK. So one of the things that LLAP does that makes this stuff happen is it has a cache. It's not the only thing, and we'll talk about much more, but cache is one thing that helps it achieve the performance. And this chart kind of shows how the size of the cache that you give LLAP changes the query result on HDFS. Now, on HDFS, when we run queries, we always bring our compute as close to the data as possible. And if LLAP can do that, it will do the same thing. So a cache miss is not as expensive as it might be if you use a cloud system or something else. So we'll see that in a second. So the red line that you see through here is what happens when you run a query in LLAP after an unrelated workload. If you run a completely different query on a different database and then run this one, well, it's not going to change. Cache is not going to change the system. But what you can see on the green line immediately is that top line that goes, that is at 100%, that's actually your metadata hit rate. So if you run queries against in LLAP, the cache will either use indices and metadata that is available in the files, like in ORC, or it will compute those on the fly. So that means LLAP all of a sudden does not have to find out what the index for the next row group anymore is, or what the min and the max of the data set is. It has all this information. It has the footer already cached. And that metadata cache you see gives you an immediate benefit, even if your cache is so small that you can't actually cache any primary data. And then as you grow your cache, you can see that the response time goes down. More and more data will be read from the cache instead from HDFS. And when you achieve 100% hit rate, you can get the query twice as fast as it was before. And it is just the cache impact in this one. So you can also see that your cache doesn't have to be 1 terabyte in size in order to get 100% hit rate. Obviously, there's a lot of queries have locality. They might be only using certain columns, or only like the last month of data, that kind of stuff. So that will help you, scale the cache. Also, we don't cache uncompressed row data or anything like that. We still keep run length encoding and dictionary encoding on the blocks that we keep in the cache. So the cache is actually quite compact, which is really useful because you want to stuff as much as you can in it. And if there's a small trade-off that you have to take to uncompress stuff before you can process it, that's still generally a good thing. All right. Now, if you don't run against HDFS, obviously cache misses become much, much more expensive. And this is what this slide basically is all about. If you're running against S3 or against WASP, Azure FS, anything like that, that cache can be really, really useful because it brings the data very close to the compute nodes. You can see the difference. There's you can easily get a 10x difference between a scan where we have to go out to a cloud storage system and fetch all the data, and a query where we can just fetch all of this from the cache. Now, when you're running against these systems, it's usually useful not just to use an in-memory cache, but also use either SD or use even the disk as a secondary cache. And LLAP can let you do that. So you can set LLAP up to not use memory, to just use a huge cache on local disk, and that will be very useful in these kind of scenarios. Something that we added very recently is native support for text in LLAP. So you don't have to run. Usually, what folks recommend is when you run on text data on comma-separated values or JSON text or anything like that, they will usually recommend that you first transform the data and put it into a columnar format that these engines can process effectively. What we're doing in LLAP is, if you're seeing these text files come up, we on the fly kind of transform it into a cache-friendly format and put it in the cache. And if you do that on local disk, like I suggested before, again, you basically get, the first query will take the hit and transform the data, and from then on out, you will get queries on the text data as quickly as you would if they're already in ORC. So that's why we're getting these, 50 times speedups on text data after the data has been cached. So that's very cool. I think it really makes it easier to handle text data, and you get pretty good performance out of it and a pretty good experience. The first query will kind of transform that stuff, and then from then on, you can handle it, and you will get pretty quick results from text data. And obviously, in LLAP, the cache that we have is coherent, which means we make sure that if the data changes or if there's new data, that we include that and that we keep the cache up to date. All right, now let's dive into how we're actually achieving this stuff. So this is the overall high-level architecture of LLAP. On the left side, you have Hive Server 2, which is the query endpoint, which is what your JDBC client connects to, and that's no different than you use Hive today. And that's what I said earlier. That's what gives you the capability to run all your same clients that you ran before, still against LLAP. The Hive server isn't going to change. What is new is we have a number of query coordinators that are spun up and permanent. And these query coordinators are kind of what limit the number of concurrent queries. Like the number of coordinators spin up limit the number of concurrent queries you can have in the system. So each of these coordinator will take one query and we'll run it end to end, and we'll make sure that all the different fragments of the query will be run and that everything is read in time and move from LLAP node to LLAP node. The coordinators and the LLAP daemons, they all run on Yarn. So we use Slider in order to maintain the coordinators and the LLAP daemons. LLAP daemons are basically compute nodes that do two things. They have an I/O subsystem, which has a shared cache for all the users, and it has query executors, a multi-threaded query execution engine that can run multiple fragments at the same time. And the coordinators will use these executors and talk to them to achieve queries. So the lifetime of a query comes in through JDBC or ODBC, will be compiled by Hive Server 2, a kind of compiled form of the query will be sent to the query coordinators for execution. The query coordinators will send out query fragments, which are small parts of the query, plus the data that they need to work on, to the executors, and the executors will start running these subsets of the query. And then they will share data as they see fit, and the coordinator will make sure that the things happen in right order. Storage can be HDFS, S3, WASPy, Isilon, whatever you want. And as we talked before that, the way you handle the cache might be different depending on what storage system you're actually running on. So how does that help us achieve query performance? What can we tell from this picture? Obviously, the fact that we don't have to spin up nodes is a tremendous speed up. We don't have to create query executors for every query that comes in. We also have a shared cache, so we might not have to read data and uncompress it. This obviously gives you a nice boost. And these query executors are multi-threaded, so you might get multiple threads running your queries, while before in the Hive container mode, each container would run a single thread. So those are kind of the things you can tell here that will make your queries a lot faster. So this is zooming in on a single LLAP daemon. Basically, as I said before, there's two aspects to it. There's the multi-threaded executors, and then there's the I/O subsystem. When a query comes in, as I said, it can run multiple fragments at the same time. A fragment has an operator pipeline that it needs to run over a certain set of data. As we spin up a fragment in LLAP, we create a pool of vectors, of column vectors that you see in the executor here. That's what the operators are going to be running on. And we will also initialize an I/O scan with the I/O subsystem. So you'll basically say, this query will need to scan this data set. You need to apply these filters, and we only need these columns from it. And that will be handed on to the I/O subsystem. And the I/O subsystem will then independently try to fill these pools of native columns vectors as fast as it can, while the executor is trying to process these vectors also as fast as it can in parallel, so there's multiple threads involved. In Hive 1 or in Hive container mode, what used to happen was we would always read a vector or read the next vector from the reader, from the I/O subsystem, and use the thread for this, and the operator pipeline would sit empty. And basically, we wait for I/O, and then when we had the vector, we would spend the CPU cycle to process this vector. And then we would go back and forth and play ping pong and lose a lot of performance that way. Now that's all gone. We're doing this in parallel now. It's much faster this way. Then the push down is nice, and it works with the metadata cache that I spoke about earlier. The metadata cache kind of knows about files, knows about what the min and max for the next stripe in the data is. It has a lot of index information about the data. So it knows where to find the data. It knows when it can skip data, when it doesn't have to read data because it can't qualify, because we know from the index that a certain filter will wipe out the entire stripe or chunk, and it can just jump over it. So we'll use the metadata cache heavily and process and use it to process the filters. Now, the cache, we talked a little bit about already. So the cache, you can have it, it's off heap. You want to have the cache off heap. You don't want to have GC pauses triggered because you're evicting a lot of data in the cache. So the cache is off heap. You can have it on SSD, and you can have it on hard disk as well, which might be useful, again, in cloud scenarios. The cache will remove the compression from the data on disk. But as I said before, we will not immediately remove run length encoding or dictionary encoding. That will be done by the decoder just ahead of time to fill it into these vectors. That means you have to do a little bit of processing on the way out, but your cache becomes much more compact, and you can pack a lot more into the cache, which is nice. And then the other thing I showed you is you can also use, this one only shows compressed columnar data, but you can also use text data, and text data will also be in parallel, be processed and put into the cache, and then we read it from the cache. Yep, I think, so again, what are the benefits here? Obviously, you have a cache and a pretty compact cache, which gives you a lot of speed up. The different threads that handle I/O and execution help tremendously because they kind of decouple having to preload data and having to process it. And obviously, that low-level pushdown can help tremendously if you can skip over a bunch of data. So those are kind of the techniques that we use to speed up queries in LLAP. All right. That's also something we quickly spoke before when we saw the concurrency graph. Every LLAP daemon has a queue of query fragments that it needs to process. And it will set them up and start them even if they're not ready yet. But it has a mechanism to preempt them and to take other fragments that might have a higher priority. And that's the kind of stuff that lets us run very, very large queries that might take hours to complete. And still, if a new query comes in, it can quickly get the resources it needs to complete. And we will give it higher priority because we know it's going to be a shorter query. And we will therefore give you the sense of that interactive sense that we want while still running some longer queries in the background. So that's very useful. All right, so that's a quick sidebar now to a slightly different topic. LLAP, as we talked about right now, is it's a full query system. It's a SQL system that can run your queries in an interactive fashion. But you can also use LLAP with other execution engines. And LLAP has an interface that lets you read directly from the LLAP daemons and kind of gives you a relational view of your data. We like to think about it as a relational data node. It kind of acts like HDFS's data node, where on every node you have a data node that serves up files. With LLAP, you can have something similar, but it doesn't serve up files, it serves up tables. The nice thing about it is if you use this and integrate it with another engine is you can get that other engine's benefit that you want or however you might want to use that system, but you retain all the things that we've built in Hive, like column level security, ACID, schema evolution. So you can bring all of that stuff to another execution engine. And Hive will take care of this, LLAP will take care and enforce these things, and then you can do your processing somewhere else. And we do this in a way where it's not just like, you might say, I can do that with JDBC as well. Let's just run a query and get the data out. But that's not what I'm talking about. Because with this interface, you can directly on those nodes in parallel on 100 different nodes, read that from LLAP and do your processing. So it's super fast. And it lets you push in projections, filters, aggregates, all of that stuff. So that if you need to bring something closer to the data, you can. So this is pretty fast and lets you integrate with it real nice. So we've done that with Spark SQL. If you want to run Spark SQL, you can run it with LLAP. And the advantage that you will get is you can also run Spark SQL just against files and against the Hive metastore. But there's a difference, because if you run it against files, you do not get that kind of row level, column level security. You have problems with ACID and stuff like that. You have to kind of, if you let Spark use those files directly, then Spark has to understand how to stitch together Delta files for transactions. It has to know how to do schema evolution. It has to know how to do column level security itself. So if that's not there, which it isn't today, you're losing out on these things and you're making trade-offs. But with this interface and the LLAP context that we've built, you can use all of Spark SQL and you can get these benefits from LLAP as well, which I think is pretty cool. In detail, how this works is on the left. You kind of see how you use it. It's pretty simple to use. You use the LLAP context and formulate your Spark SQL query. What happens under the hood is that we have some compiler hooks that will say this part of the query will push into LLAP, which might be nothing. It might just be reading the tables, or it might be pushing filters and projections in to get it a little faster. And then we will go to the metastore, to the Hive metastore, and kind of get authorization to read certain splits from LLAP. And this is also what generates access plans that enforce column level security and all of that stuff. We hand that back to Spark, and then Spark can directly go out to the cluster on the same cluster nodes where LLAP runs in like 100 different nodes, read this data set that it needs in parallel and continue processing it. So again, you get kind of the benefits of security and schema evolution, ACID, all of this, and then you're processing it in Spark like it's native data. So this is pretty nice. Okay. Now the final part of the presentation, I just want to talk quickly about how you can try out LLAP and some operational concerns that you might have. So first of all, availability. First version was shipped in Hive 2.0. Hive 2.0 has a lot of fixes. Hive 2.1 is definitely something you want to be using if you really want to play with LLAP. In Hortonworks, we've shipped LLAP with 2.5 as a tech preview. 2.6, which has just come out, includes a GA version of this. So now we do support LLAP for production workloads, which is cool. I'm very excited about that. Here's how you set it up. Like, I don't know if you guys have seen versions of this talk before from a year ago. There used to be now 10 different slides on how to configure LLAP, because in Apache, everything you do has like thousands of config knobs. We tried to take care of all of this and just hide it behind a single wizard. So if you use Ambari, and if you already have a cluster set up, all you have to do after you upgrade to at least 2.5x is to enable interactive query with that switch on top. You have to make a few choices, which are very simple. You have to say which yarn queue you want your LLAP to run in. We will take the default queue if you want to. You have to say how many nodes you want to use, and you have to say how many queries you want to be able to run in parallel. So that's kind of that's what spins up the coordinators we've talked about in the architecture slide. And that's it. You hit enable, and it will do the rest for you. It will do all the memory computations, all the setup. It will figure out how much cache to use, how much, what's a good size of executors per node, and all of that stuff. So it will set up security, everything else. So we've tried to make it as easy as possible. I think with this is pretty nice. Shouldn't take a whole lot to kind of just at least start playing with it. If you have a little bit of capacity in your cluster, all you need to do is hit that button and see what happens. At the top, it says it requires yarn preemption. That's basically because if you have a very busy cluster and we want to start up LLAP, we want to make sure we have the opportunity to kill some workloads and actually start up LLAP. Otherwise, LLAP might not come up because yarn will not give us any capacity. That's basically what's hiding behind that. So that's one way of getting an LLAP cluster spun up. Another way of doing that is with the Hortonworks Data Cloud. So you might have a production cluster, and it might be the case that nobody wants you to take half of the cluster to try playing with LLAP. It's understandable. Maybe the best way to do it is in the cloud. So it's pretty easy to set up once you have your cloud controller set up, and that's on the Amazon Marketplace. All you need to do is kind of fill out this little form here. Pick the template type of EDW analytics with Hive 2 LLAP. Say how many nodes you want and what instant types you want, and hit go. And then after a few minutes, you will have your LLAP cluster set up and configured and all of that. Obviously, you can use RDS for your metastore, so you don't have to maintain your own Postgres or MySQL instance or whatever it is. And it's easy to set up an S3 bucket with the data warehouse that you can use for this kind of stuff. So it's a super simple way to, either play with LLP, get started with it, or even just use it as a production environment. And this is in HTTP 2.6. Now, once your cluster come up, one simple way of monitoring it is each of the LLAP daemons has a little UI that kind of gives you information about what's happening on that daemon right now. It will tell you how big your cache is, what your cache use rate is, what your metrics are. Just a quick overview on each different node. It has a much richer data set if you want to integrate with JMX directly. And if you're using HTTP, there's also a bunch of default Grafana monitoring dashboards that we ship with LLAP. So here it's just the overview list of the dashboards that are available. These dashboards have a wealth of information to show you how much cache you have, how many tables you have, how many partitions you have, what's the use of your cluster, how many executors are currently in use, all of this stuff. So it really helps identifying bottlenecks. It helps with capacity planning, and give you a good overview over what your cluster is actually doing. If you want to, on the other hand, find out what a single query was doing instead of kind of getting an aggregate view of your system, the test UI has a lot of information for LLAP available as well. So you can look by query now. You'll see a graph of kind of what the stages of the query were. And for each query, you can get a lot of LLAP data. You can see how much that particular query was caching, how much time that particular query took, and a whole other stuff, which might help you find out why that particular query was slow, what else you could be doing to make it faster. All right, what's up next for us? So there's a few operational things. Like what we're focusing right now in LLAP is we've just shipped 2.6, and we've done a lot of work to make LLAP production ready, to polish it, to put monitoring in place, and all of that stuff. One piece of feedback that we've gotten from folks is that they want more controls over who gets to run queries and make sure that there is reserved capacity for some folks, and kind of the thing that we've built where we try to make sure that the system remains interactive and we do schedule multiple queries together. That stuff needs to be expanded to give you even more controls for for truly multi-tenant LLAP clusters. So one thing we're looking into is more fine-grained workload management, having reservations so that for a certain group of users, you can make sure that they always have 20% available of the cluster to themselves so that their queries are fast. Guardrails is another thing that we've been asked about, basically making sure that we protect the LLAP cluster and make sure that if someone runs some ridiculous query that scans 20 years of data and it will take months to do that, that we actually don't let those queries in. So that you have kind of controls as an admin about the system like that. Or that after half an hour you can kill any query because you really don't want people to use the system for their heavy lifting ETL tasks, stuff like that. And then finally, admin tools. We're working on a set of tools to make sure that it makes it even easier for you to identify kind of how to make the system even perform even faster. It might recommend optimizations at the physical layer to you. It might recommend additional capacity on LLAP or maybe a different cache configuration for you, that kind of stuff. All right, so in summary, what I hope you take away from this is, A, LLAP is fast and awesome. B, it has an API that lets you integrate LLAP with other execution engines if you choose to do so. And C, we've done a lot of work to kind of integrate it with the ecosystem, with monitoring, with Ambari, with the cloud and other stuff. And with that, I hope I still have some, I have about 5 minutes for questions. We're going to pass around the microphone. It makes it easier to hear the questions on the recording.
Thanks. I think you've said that if we have Hive reading a lot of CSV files, then this will generate an in-memory, potentially hard disk-backed cache of that in a structured format. Is there a way to warm up that cache, or if you turn your whole cluster off and then turn it off again, turn it on again, do you have to wait a few days and run through some sample queries?
That's a good question. If you turn off if you kill your cluster and bring it back online, it wipes out your cache. So there's ways you can preload the cache, but you have to run these queries again. So you have to run an analyze command or something like that. It's actually something that I think there are some Jiras for exactly that case. There's a demand for more cache control primitives. Those are not quite there yet. So yes, if you bring it back up, you have to run. We recommend usually running analyze table, which will generate statistics about the tables and will do these transformation and caching for you ahead of time on the tables that you think are valuable to do that on.
Would you recommend that today, or would you say for now we should pre-process into awk files then?
For text? No, I mean, it depends on your environment. But if you, for instance, bring it up every morning and you have some time to run these queries, that's fine. It will work just fine. If you already have a process that is transforming the stuff to org, there's nothing wrong with that. I mean, long-term storage in org is also more compact than text, so there's other benefits. There's other considerations that are involved in that. So, but yes, you can definitely, either leave the cluster on and just let the cache take care of itself, or kind of every morning before folks start working with the data, do some cache warming for them. That's definitely possible today.
Cool, thanks.
And yes, I'm sure there will be more cache primitives coming pretty soon. Actually, that's something that I didn't include on the future work, but it's actually something that we get a lot of requests for good reason. Thank you for the question. I hope that answered it. There's another question.
So right now, at the moment, it's not possible to use 2 different yarn queues for different types of users with LLAP. Sorry.
We made that name as complicated as possible. LLAP, by the way, stands for live long and process. And like I showed you, like some super simple ways of bringing LLAP up. That way, with that stuff, you cannot set up an LLAP that spawns multiple queues or stuff like that. You can do that, but you're basically in the weeds. Like you have to configure the whole thing yourself, which is possible. So the software supports multiple LLAP daemons in multiple queues at the same time, There's software even support from a single Hive server to use multiple on those, or to use different Hive server tools. All of it is completely supported in the software, but all of the tools that I've shown don't do that. So you have to really roll up your sleeves and start configuring the system yourselves, which is quite tricky, trust me. But it's possible if you want to do so. The way we actually want to go about this is to kind of build these controls about workload management into LLAP itself. The reason for that being that with LLAP, we want to make much more fast and fine-grained decisions for workload management than Yarn typically lets you do when you scale up and down clusters and stuff like that. So it's a little bit of a different use. But if you feel adventurous, you can go in there and set up multiple LLAP queues yourself.
What are like typical Yarn container sizes that you give to LLAP, to the query executors, or also like the coordinators? Okay.
So again, the tools that I've shown make these determinations for you automatically. And the way they try to do is they try to use the entire node for LLAP. So we recommend if you have a 100 Yarn cluster and you only want to use 20 nodes or 20% for LLAP, do not kind of spread out your LLAP over all the nodes, but kind of use 20% of the nodes and use them up fully for LLAP. And then what we do is we make sure that we have enough working memory for executors to kind of use up all the cores you have on that machine. So we're trying to make sure that we can have, if the system is fully loaded, we can have one fragment per core running, and that's how we kind of scale the working memory. So we give about 2 gigabytes for each of the fragments, the executors. And then the rest of the memory we use for cache. That's how we set up the system today. And we found that to be quite effective. I just got to note that my time is up. I'm here for questions if you like. I'm happy to answer them. But thank you all for coming. Appreciate your time.